as a supplement, let's derive this formula for torsion that computes torsion in terms of a triple scalar product of the first three derivatives of r and the cross product. So as we'll recall from a previous video, we have the Frenet Serret formulas for the derivatives of the tangent, normal, and binormals. Also recall again that if we take the derivative of the arc length function, that's the same thing as the derivative of r prime. And we also need to recall our tangential and normal components of acceleration, namely the tangential is s double prime, and the normal component is s prime squared times curvature, kappa. Or you could read that as the length of r prime squared times kappa. Okay, so first thing we're going to do as a kind of typical thing for differential geometry, we want to get a formula. We're going to differentiate something. So let's go ahead and differentiate this and figure out what r triple prime is. And again, if you look back at how torsion's defined, it's not unreasonable to think that a formula for torsion ought to involve a third derivative. So it makes sense to be doing this anyway, even if we didn't know what the formula was. Okay, so first of all, we differentiate s double prime t. The product rule says this will be s triple prime t plus s double prime t prime, right? Because we take the derivative of the first thing, second thing left alone, plus the first thing left alone times the derivative of the second thing. Then we'll add this to, and we need to differentiate this guy here. So I'm going to kind of leave this somewhat undone. We have the derivative of whatever s prime squared times kappa's derivative is, and then we times n, and then we have s prime squared kappa n prime. Okay, so there's the result of our differentiation, the product rule. Okay, we'll kind of underline so see where those correspond to. All right, now let's use our Frenet Serret formulas. So we have s triple prime t, and we know that the derivative of t is going to give us, let's see, we'll have s double prime times kappa times the length of r prime. I'm going to write as s prime here times n. Right, so that's just taking this guy and replacing it with what the Frenet Serret formulas say. Okay, and then let's add to that. We have our kind of what will turn out to be a garbage term here times n, and then I'm going to replace n prime with what the Frenet Serret formulas say about it. So it has two terms. The first one, being a negative, right? So we have minus, and it looks like we have s prime squared times kappa times negative kappa, and then another copy of s prime. Remember, the length of r prime is the same thing as s prime, so we actually have a cubed here times t. And then for the next term, we'll have our s prime squared times kappa and times a torsion. And oh look, there's another copy of s prime. So again, we'll have it cubed there times b. Okay, so we just use the Frenet Serret formulas to replace t prime and n prime. Now let's rearrange things just a little bit. Try to gather some stuff together. First of all, what's next to t? Well, we have an s triple prime next to t. Also next to t we have this stuff in this term, so that's minus s prime cubed times kappa squared, and so there's our coefficient of t. Alright, now let's gather stuff next to n. So what's next to n? We have this stuff here, so that's s prime times s double prime times kappa plus this garbage here, s prime squared kappa, derivative of that. Okay. And then finally, let's take care of what's next to b, and so that looks to just be s prime cubed kappa tau, curvature torsion, times b. All right, so there we go. We have this rewritten. So we just differentiated the acceleration to get r triple prime and use Frenet Serret to write it in terms of t and b. So it's complicated, but also straightforward where it came from. Now, let's recall what is r prime cross r double prime. Okay, we need that. So kind of on a separate track, this would be r prime cross, well, let's see, what is r double prime? According to our tangential normal components of acceleration discussion, it's s double prime t plus s prime squared kappa n. But wait a minute, if you think about it, t is parallel to r prime, so when we cross product, that term goes away. So we just have r prime cross the second bit there. So this is s prime times kappa times r prime cross n, just factoring out the s prime squared and kappa. But r prime itself is the same thing as length of r prime times t, right? That's a decomposition into magnitude times direction. But length of r prime is the same thing as s prime. So we can rewrite this yet one more time as we have s prime from here, but we get an extra one, so that's s prime squared kappa, and then we have t cross n. Oh, but we know what t cross n is. Remember our right-handed system, t and b. The definition of b actually was t cross n. Okay, so long story short, what do we have? We have that r prime cross r double prime is the derivative of s cubed times kappa times b. Okay, now let's put things together. Okay, so let's take the triple scalar product r prime cross r double prime dotted with r triple prime. All right, well, we know that's s prime cubed kappa beta dotted with, behave ourselves, okay, and then we have our big old mess up here for what our triple prime is. And so I'm just going to write it as stuff times t plus stuff times n plus, and then what actually matters, s prime cubed kappa tau b. Okay. Now keep in mind that b is perpendicular to t and n. So if you take b and dot it with a t, you get 0, and b dotted with an n is 0. So in this, these guys don't factor in at all. All that garbage collapses out. And all we're left with is s prime, well, let's see, we have 3 copies here and 3 more, so that's 6 copies. We have kappa, I have a copy here and a copy here, so we have 2 copies of kappa. We have a copy of tau, and then b dot b, well, that's just 1, because that's the length of b squared. b is a unit vector. Well, isn't that handy? If we stare at this right here, we're very close to having a formula for tau. In fact, let's solve and find out what is tau. Tau should be r prime cross r double prime dotted with r triple prime divided by s prime to the 6th kappa squared. All right, well, let's unfold what this is. We have r prime cross r double prime dotted with r triple prime. I'm going to rewrite s prime as the length of r prime. Those are the same thing. So we have that to the 6th power. Kappa, we have already had a cross product formula for that. Remember, that was r prime cross r double prime over the length of r prime cubed. So if I have kappa squared, we'll have r prime cross r double prime length squared over r prime to the 6th. So that's just using that formula for kappa. The r primes cancel, and then there we go. We have our formula for torsion. Torsion is the triple scalar product of the first three derivatives of our parameterization divided by the length of the cross product of the first two derivatives squared. So there's a nice clean formula for torsion.